certain important features about qualitative aspects of equilibrium. We'll today start to take a look at quantitative aspects of equilibrium. In other words, how to do calculations on equilibrium systems. Directive: to do calculations on equilibrium systems correctly, as in doing calculations on any chemical reaction system correctly. What do you need to know how to do? It's called STO stoichiometry. How about that? And what is your stoichiometric guide for any chemical reaction system? The equation for the reaction. So take note. At any time you need to deal with a chemical reaction system, practically speaking, what you always want to do first is what? Write the equation for the reaction. And as we have already reminded you, or at least introduced you to, usually in order to write an equation for a reaction system, what do you have to do with the reaction system before you can write this equation? You have to construct a PSI. Because if you don't know what's in that system, there's no way you can write an equation for any reaction that will occur in the system. There's no way you can understand any chemistry that occurs in the system if you don't know what's in the system. This isn't voodoo or magic. In any case, with that, we pick it up from our point of departure, which was calculation applied to the I2 distribution equilibrium that we looked at between the immiscible liquids toluene and water. I2 not polar, toluene slightly polar, water highly polar, highly electric in character. Upshot, I2 is a lot more soluble in toluene than it is in water. In fact, you did experiments on this in 45 laboratory, the solutions experiment. You didn't use toluene in that exercise, but you did use a material whose polarity is similar to that of toluene, namely methylene chloride. The formula was CH2Cl2. Remember that? How do you think the solubility of I2 in methylene chloride, the liquid you used to investigate this solubility in 2045 laboratory, compares to the solubility of I2 in toluene? In which liquid? Toluene or methylene chloride? Is I2 more soluble? Toluene. More soluble than toluene. That's because toluene is less polar. How do you know that? How do you know from methylene chloride that it's more polar than toluene? I heard the word. Say it louder.
Structure.
Structure! What is the structure of methylene chloride? You did this in 2045. It's tetrahedral. So with that, you're forced to recognize that the carbon-chlorine bonds are, practically speaking, on one side of this tetrahedral molecule versus the carbon-hydrogen bonds. And the carbon-chlorine bonds are a lot more polar. Why? The electronegativity difference between carbon and chlorine is greater than the electronegativity difference between carbon and hydrogen. Not a big difference, but somewhat greater. In any case, for the distribution of I2 between the immiscible liquids toluene and water, here's the distribution equilibrium constant. We purposely write it like this rather than I2 water up top because we are usually more at ease in dealing with numbers that are larger than 1 calculation-wise compared to numbers which are smaller than 1. Now if I invert this, I still have a perfectly legitimate equilibrium constant. But if I invert this, what's the value for the equilibrium constant? 1 over 70. Do I like this better? Now then, next part of the puzzle. Question 17.9 says, if we dissolve 0.500 grams of I2 in a mixture composed of 900 mils water and 100 mils toluene, calculate the mass of I2 in each layer at equilibrium. Well, we're using a volume of water in making this mixture which is 9 times greater than that of toluene. Nevertheless, we can still readily conclude that the bulk of the I2 will still wind up in the toluene layer. Why is that? Or let me ask the question this way. If in mixing water with toluene, what has got to be the volume ratio of water to toluene? The volume ratio of water to toluene, if most of the I2 is going to wind up in the water layer.
70 to 1.
It's got to be bigger than 70 to 1. That's what that distribution equilibrium constant tells us. Now then, the next part of the puzzle is to realize the distribution equilibrium constant is expressed in molarities. Indeed, we've already realized equilibrium constants are always expressed exclusively in molarities and or partial pressures. That's it. So, we've got to establish a relationship between mass of I2, because we're trying to find out the mass of I2 in each liquid at equilibrium. Whereas the equilibrium distribution constant is expressed in molarities. Now, when you want a relationship between mass and molarity, what property of the material do you have to pay attention to? You did this in 2045.
Formula?
Formula mass. Same as molar mass. Now, the symbol usually used for molar mass is fancy squiggle M. That's a fine symbol, but I'm not so good at drawing this on the board, so I'll just use FM for formula mass. And the units on formula mass are grams per mole. But these terms have units of moles per liter. So I need to take formula mass and invert it. But the beauty of this calculation is to realize that I'm going to have inverted formula mass for I2 in the numerator and inverted formula mass for I2 in the denominator. So I really never need to calculate any actual concentration. I don't need the value for the molar mass of I2. Because this term divides from top and bottom of our expression. But I realize if 0.500 grams minus X corresponds to mass of I2 in the toluene layer, then inverted formula mass times this quantity divided by the volume expressed in liters gives us molarity of I2 in toluene up top. The same applies to getting molarity of I2 in water down below. Well, so what do you wind up with here? A first-order algebraic expression containing one unknown. You've got to be able to solve this. There's nothing to it. And you get this. Which means the mass of I2 in the toluene layer is 0.500 grams less this. Done. Now, we asked about solubility of I2 in methylene chloride versus toluene. A similar question. For toluene water, the equilibrium distribution constant with I2 being the solute is 70.0. What if I use carbon tetrachloride instead of toluene? How would the value for the equilibrium distribution constant compare to 70.0? Would it be greater? Yes, why? Because carbon 10 is strictly nonpolar, like I2. It's 80 for carbon 10. I used to do this demonstration with carbon 10, but then carbon 10 was found to have carcinogenic properties, and so we prefer not to use it and went to the less dangerous material, toluene. All right. Now, let's get further into the subject of doing equilibrium calculations. Now, what we're going to look at right now is in the notes, but I'm going to ask, please, that as we go through this problem, don't look at the notes. Look at what we have on the board, because you always can revert to the notes later. Because what we want you to do is to go along with us in the analysis of this problem. The thought that underlies tackling the problem. Because that's what you need to do when you've got to solve these problems on your own. We shall imagine making a mixture of 2/100 of a mole of 3 sig figs of nitrogen with 3/100 of a mole of 3 sig figs of hydrogen in a 1.00 liter flask, which initially contains no ammonia. And we are instructed to calculate the value for the equilibrium constant. So, this problem involves a reaction, so I write the equation for the reaction. There it is. Could I have written this reaction equation in the other direction? Would it still be a legitimate equilibrium if I write it in the other direction? Of course. But I prefer to write it in this direction simply because we're starting with nitrogen and hydrogen, and initially we have no ammonia. This guarantees the recognition that nitrogen and hydrogen have got to react with each other to make ammonia, because we don't have any ammonia initially. So rather than writing in the opposite direction, I prefer to write it this way. The next part of the puzzle is the given at equilibrium 0.190 moles of nitrogen are found to be present at equilibrium. I don't know why I have that in there. And recognize, please, that a number of times when I introduce you to problems like this which involve calculation, I will try to keep the numbers part of the puzzle as simple as possible, because I want you to focus on the chemistry. Because if you can do the chemistry, you can always do the numbers. Point: I've purposely considered this reaction to occur in a 1.00 liter flask, because in a volume of 1 liter, how do molarities and mole amounts compare? They're numerically equivalent. But if I change volume to anything other than 1 liter, then that statement we just made isn't true. So that would involve more arithmetic. So by stipulating this to take place and be established in a 1 liter flask, we're going to simplify the arithmetic so we can focus on the chemistry. All right, equilibrium reaction equation, K expression, 0.190 moles of nitrogen found to be present at equilibrium. That tells us how much nitrogen got used up to get to equilibrium. 0.010 moles. Now then, remember what I said about to do equilibrium arithmetic? To do any calculations on a reaction system, you have to pay attention to stoichiometry, and the equation for the reaction is your stoichiometry guide. Did you learn how to read equations for reactions in 2045? If you didn't, let me read this equation to you, right here. Because an equation for a reaction, if you've not yet realized such, is a recipe. It's an if-then clause. Under no circumstances is it a guarantee of anything, nor does it indicate how much stuff you have, period, zero, zip. For example, did you ever see a recipe on the box of a pancake mix? The recipe might say, dump the contents of this box in a large mixing bowl. Okay, so you did that. Got your big mixing bowl. Stir in a quart of milk and 3 eggs. So you open up your fridge, you got the milk, plenty of milk, you got a gallon, you pour out, measure a quart, pour that in there. Then you go into your egg carton, also in your refrigerator. And you'll find out, oh, it says 3 large eggs. Okay. You go into your refrigerator, you got large eggs. That's what you bought at Publix. But people have already eaten breakfast and used all the eggs except 2. And you already added the quart of milk and the entire package contents. Can you now complete following the directions? No, because you don't have 3 eggs, you only got 2. So, we're illustrating to you that the recipe on the back of that package in no way allowed you to know how much milk you had and how many eggs you had, did it? Just like an equation for reaction. As written, this statement says, if a mole of nitrogen reacts completely with 3 moles of hydrogen, then I have a chance to make 2 moles of ammonia. If I read it the other way, if 2 moles of ammonia falls apart, then I can make a mole of nitrogen and 3 moles of hydrogen. But this tells me nothing about the conditions that must be established for this reaction to occur, nor does it tell me anything about the amounts of nitrogen, hydrogen, and ammonia, which I may or may not have. But this does. All right, back to the recognition that 0.010 moles of nitrogen was used to get us to equilibrium. So how much hydrogen had to be used? 0.030. So how much hydrogen will be present at equilibrium? This less 0.030, which if I've done my arithmetic correctly gives me 0.270 moles. And finally, although we could have done this arithmetic next and then gone back to this, if I use 0.010 moles of this, along with 0.030 moles of this, how much of this did I make? 0.020. Don't mess up the significant figures. And recognize we determine this value and this value from the stoichiometry defined by and established by this reaction equation. So now we put in the numbers. You can put in the numbers. And what do you get when you put in the numbers? I wrote it down here someplace. I think it's 0.11. Wonderful. Now let's ask a related question. The same reaction system, same temperature, but we're going to consider different quantities. If, for the K expression for this system, expressed in this fashion, gives a K value of 0.11. If I consider this equilibrium system, what will the K value be? Will it be the same? Will it be larger, or will it be smaller than 0.11? Do you recognize that to get the K value for this expression, this reaction, I've got to take the K value I've got up top and do what to it? Square it. How about that? So to get the K value, I've got to square 0.11. If I square 0.11, do I get 0.11? Do I get a number bigger than 0.11? No. Because when you take a fraction of a fraction, you wind up with a smaller number yet. Okay? Well, just for fun, if I'm interested in the K value for the very same system, which involves the possible generation of 1 mole of ammonia, so I'll write the equilibrium reaction like this. Now what will I do to get the K value? Take the square root. And if I take the square root of 0.11, will I get a number bigger or smaller than 0.11? Bigger. How about that? Okay, next. We're just plowing through the stuff in chronological sequence that you find in the notes on these aspects of equilibrium calculation. Hydrogen with carbon dioxide, under appropriate conditions will react to make water vapor and carbon monoxide. Now, as we know, carbon monoxide is toxic to the human system. Nevertheless, carbon monoxide is quite an important industrial material. It's used for a lot of purposes. And this provides a method by which carbon monoxide can be made. Now notice, from a stoichiometry standpoint, this reaction system is simpler than this reaction system. Because here, the coefficient ratio is 1 to 1, 1, 1, 1, 1. Okay? So let's go back and look at this one for a moment. If I have this system at equilibrium, which we're going to study in greater detail when we go to challenge problem 17.1. If I have this system at equilibrium, and it's contained not in a flask, but in a vessel whose volume can be varied, like a piston cylinder. There's my $64,000 Van Gogh replication of a piston cylinder. Okay? Well, I can take a hold of the handle on that piston and push it into the cylinder, which means I've applied pressure to the contents and reduced the volume which they occupy. Or I can take a hold of the handle and remove it up inside the cylinder and increase the volume, and in so doing reduce the pressure applied to the contained materials. So if I've got this nitrogen, hydrogen, ammonia in a piston cylinder gadget, and it's at equilibrium, and I reduce the pressure, I increase the volume occupied by this system. Does that change the concentrations? Sure. Volume's now bigger than the liter. So all the concentrations change. And consequently, at the very instant at which I apply this change to that system, I will not change the value for the equilibrium constant, but I will destroy the equilibrium. And what does Le Chatelier's principle tell us? If you destroy an equilibrium, if at all possible, the system will react to counterbalance this destruction of equilibrium and try to get back to equilibrium, because it's the most stable thermodynamic state in which the system can exist. Textbooks have a nasty habit of referring to something like this as a shift in the equilibrium. No respectable equilibrium will ever shift. It's the most stable state the system can be in. When you apply these changes like this, you've destroyed the equilibrium. So how in the hell can something shift if it ain't there? These people need to understand the language they use. I mean it. If we're going to succeed in communicating successfully to you folks, whose purpose is to learn this stuff, we better choose our words and phrases carefully, so that they communicate sharply and clearly. I reject a stupid statement like that made by textbook authors. Now, one more reason why I don't use these general chemistry textbooks in this gathering. My observations serve to indicate any organic text you buy today is a good book. You can actually learn organic chemistry if you're a serious, dedicated student of chemistry without ever going to class. Now, forbid that you act like that. But you can do it. Analytical chemistry the same way. Physical chemistry. But for reasons which I just cannot fathom, general chemistry textbooks across the board are still trash. It's a shame. Tell you another thing. Of all the disciplines of chemistry to teach, this is the most difficult. Because in general chemistry, everything is fair game. In order for me to hope to be a successful communicator of this stuff, a so-called teacher, I've got to know organic, I got to know analytical, I got to know physical, I got to know theoretical physical and experimental physical, I got to know inorganic. I need to know all this stuff. That's not easy. That's a lot of stuff for which to be responsible. And I will tell you, in my, oh my, how long have I been doing this now? 45 years. I have done, for the most part, a great deal of work to build up my knowledge of these various disciplines of chemistry, to support my ability to present this wonderful stuff to you folks. Hey, I love it. And because I love it, I'm not using these bad books to try to get this stuff across. The notes that you are using are in serious need of rewrite, but it's the best I have at this point. I'm trying to find the time to rewrite. I'll get there when I can. I'll do a lot of things, but quit ain't one of them. Okay. So if I got this at equilibrium and I increase the volume, at that point the equilibrium is destroyed. What reaction will take place if I in fact destroyed the equilibrium by increasing the volume? Remember, I didn't put anything new in the system, nor did I take anything out of the system. I just changed the volume, which changed concentrations. So the only reaction which can occur to get us back to equilibrium is this reaction going left to right as written, or right to left as written. Which will take place based on the volume increase? Right to left. A simple way to realize that is, as things stand on a ratio basis, this represents 2 moles of ammonia, 2 moles gas, I should say, versus 4 moles gas, right? Doesn't matter that these are different or same. 2 moles, 4 moles. Do you think it's the case that if I up the volume, I will tend to increase mole count? Because more moles of stuff can live more easily in a larger volume? That's what we're doing. You go to the side of the fence where more moles of gas are represented when you up the volume. Now, if you reduce the volume, it goes the other way. Now, this is explained more elegantly and in greater detail as a consequence of the applied change to the concentrations in the notes. I hope you've looked at it. But again, the simple way to get at this is, as we said, if you up the volume for a gas system, I proceed toward more moles of gas. If you reduce the volume, I proceed toward fewer moles of gas. And this is also dealt with quantitatively in the notes with this term. How many of you saw that term in the notes? Called Q. Q is an expression written for a reaction which is structurally and compositionally identical to the equilibrium constant. Q for this is this. What's the difference? K involves exclusively equilibrium values. Q involves any possible values. We'll take a further look at Q when we get to that system. All right? Back to this. Now then, question 17.4 regarding this system says, if I study this at a temperature and pressure at which this gas has a behavior describable by this equation. What is this equation? The ideal gas law. What does ideal mean? You did this in 2045. What does the term ideal mean when it's applied to PV equals nRT? What's it mean? Under what conditions do gases behave ideally?
ATM.
High temperature, low pressure. Why is that true? Why do gases behave ideally under, relatively speaking, high temperatures and low pressures? What are you trying to defeat to establish ideal behavior? What?
Intermolecular forces.
Intermolecular forces, and what else? Actual molecular volumes. How many of you in 2045 look at the van der Waals equation, which includes the correction terms A and B? One corrects for attractions, the other one corrects for actual molecular volume. So I repeat the question. If I study this equilibrium reaction at a temperature at which the behavior of this stuff in the gas phase is describable by this equation, can I now say matter-of-factly that all the other gases in this system will also show behaviors describable by this equation? If water vapor behaves ideally, will hydrogen vapor, CO2 vapor, and carbon monoxide vapor in the same system also behave ideally? Yes. Why?
Because hydrogen has boiling point.
Because intermolecular attraction forces among and between water molecules are a hell of a lot greater than intermolecular attraction forces among and between the other gas components of this system. That's a consequence of the highly electrical nature of the highly polar water molecule, coupled with the fact that the water molecule shows the strongest type of intermolecular attraction force, which is known as what? Hydrogen bonding. How about that? And if you didn't know about hydrogen bonding, if you didn't know the water molecule was highly polar, but you had a data table of boiling points, how could you know that if this is showing a behavior describable by this, then these other gas components will also show this behavior? You're looking at a data table of boiling points. This converts spontaneously to the liquid phase at 100 centigrade or 101 centigrade. Got to go just above 100 centigrade, okay? How about boiling point for this? You think it's lower than 100 centigrade? You got to get this stuff damn near to absolute zero to liquefy it. How about this? Lower than 100 centigrade. A hell of a lot lower than 100 centigrade. How about this? A hell of a lot lower than 100 centigrade. Bingo. And just for fun, did you realize in 2045 that this is an energy equation? Did you learn that? This is an energy equation. Pressure volume product gives energy. Energy. And in our gathering, we will refer to pressures for gases in atmospheres. Today, the standard unit for pressure is the bar. But I don't think the data I have in the notes correspond to bar. When such becomes published by the National Bureau of Standards, so I don't have to go through the data and do a bunch of calculations to change it, I'll stick with atmospheres. But we're not going to have much inaccuracy in what we do. Because 1 atmosphere exactly is 1.01 bars exactly. So there's only a 1% difference. We'll live with that. pressure in atmospheres times V, say liters. Liter atmospheres. That's an energy unit. When I started graduate school, working on my master's degree in little old University of Toledo, I had a physical chemistry course on kinetics, taught by a physical chemist who was a graduate of the University of Tennessee. This guy established himself among the ranks of the very poorest instructors I've ever had the misfortune of being with. He gave us a direction to read some stuff in the book. I read it. I read it and I read it again. It didn't translate to me. It had to do with collision theory versus transition state theory. Very important physical chemistry considerations for kinetics. When we got back to class the following day, he asked if we had any questions on what we had read. I raised my hand. Called on me. I said, the stuff which I read on page so-and-so, I don't forget to remember the page number. I said, I'm sorry, I've read this 3 or 4 times, I've mulled on it, and it just doesn't translate. Would you please provide some explanation? He opened the book, glanced at the page, looked back at me and says, oh, that's clear enough, and closed the book. I said, you son of a bitch. I got 0 explanation. None. He then gave us a problem, a set of problems, where we had to calculate a bunch of activation energies. Now, I think you learned in 2045 that energies are usually calculated in joules. Kilojoules or joules, okay? Back those days, we used calories and kilocalories. Doesn't make any difference. Ha ha! I said, I'll fix you. I calculated every one of my energies correctly in liter atmospheres. Every one I had was calculated correctly. He took off half credit. His explanation was, we do not commonly express energies in liter atmospheres. I let it go. I figure I dug the needle in at least a little bit. Because he had to do the arithmetic to check my work, all of which was right. I said, S.O.B. See? Don't forget that I too was a student. And don't forget that I still am. Now then, we talked about this. There's a simple question 1711 based on the data supplied for this question using this expression, because we're going to consider studying this at a temperature at which all component gases behave ideally. We'll calculate the temperature. It's 1218 K. Do you think this will behave ideally at 1218 K? Absolutely. All right. Now then, let's look at this one. You learned in Chemistry 2045 about a topic called thermochemistry, a highly inadequate introduction to thermodynamics. Because what we need to know about a reaction from a thermodynamic standpoint mainly is whether or not, under the conditions the reaction is being studied, can it go, yes or no? And if it can go, it's said to be spontaneous. And you cannot get at reaction spontaneity strictly from change in thermal energy, delta H. There's another reason why these general chemistry books are dumb. They've introduced you to half of what you need to know about thermodynamics. And then later on, before you get to the chapter on thermodynamics, they ask you a bunch of questions that require you to understand all this, which you can't possibly do because they haven't mentioned it. So let's look at this reaction equation. It shows the coalescence of NO2 molecules into N2O4 molecules. And by the way, this clock is the right one. And we don't finish till 12:35. This reaction is exothermic, guaranteed. Why can I say that? Did you learn in 2045 that the most important thing you find out about a reaction system, if you find it to be exothermic, is that you're looking at a reaction for which bond improvement is occurring. And that reaction is exclusively bond forming. So I leave you with this assignment, which we'll start with when we reconvene, I guess next week, Wednesday, because this place should run on Labor Day. Forget that. I want you to write Lewis pictures for this molecule and this molecule. Lewis pictures. And see if you can determine what bonds form when this reaction takes place. Pick it up from there next time.